Hi everyone, welcome back. And today we are going to build an AI agent that will be totally RAG based, and RAG stands for Retrieval Augmented Generation. So, before we start building our AI agent, we need to understand what Pinecone is. So, Pinecone is basically a vector database used to store your vector embeddings inside this Pinecone vector DB. So Pinecone is an open source vector DB that lets you to store your vector embeddings in a separate vector database. So it's really easy to understand this vector database, and it's very helpful and useful for storing your vector embeddings in a Pinecone vector database. So there are bunch of available documents for Pinecone. You can start understanding what Pinecone is. So our first concept in Pinecone is to understand what an index is, how to prepare the data, and how to upsert and ingest our PDF textual file, unstructured data, and all our textual information in our index. Then once our data is ingested into Pinecone, we will search our data using some index.query and Pinecone API methods available on this Pinecone website. Then we can improve our relevance and search query by using some re-ranking and lexical search algorithms. So let's get started. So the first step is to create an index. So in order to create an index, you need to understand how to create an index and what index is. So index is basically to store your information in a namespace. So there are bunch of available indexes that supports AWS, GCP, and different cloud services platforms to have your embedding stored in those vector databases. Like AWS has its own vector database, GCP, and Azure. So that's a different concept, and it's an advanced concept, but we won't be covering that. We are just starting with the basic concept. So the first step is to understand how to create an index. So in there are multiple available languages to create an index. So we will be using Python, and to create an index in Pinecone, we will use the Pinecone dependencies and the Pinecone library to store some data and create an index. So the first step is to import these libraries and use your own API key. So when you sign up for Pinecone, you will go to this terminal, and once you have this terminal logged in, you will see a bunch of resources over here, like get started with Pinecone, how to create an index, how to create a RAG and QA search model, multimodal search, semantic search. There are many available resources on Pinecone. So the first step is to see this dashboard and understand what this dashboard provides us. So once you log in, you will see this dashboard. We have this get started, our database, we have number of indexes created, and I will show you how to create an index. Then we have the API key over here. So you have to create your own API key, and once your API key is created, you will use it in your Python SDK environment. Also, Pinecone provides us to create 5 indexes, and the limitation of Pinecone is if you have the trial version, you can create up to 5 indexes, but as you go towards the pay as you go, as you pay, you can create multiple indexes by following some Pinecone pricing architecture. So we will be using the free trial version of Pinecone. and it allows us to store 2 GB of data, store up to 2 GB of contextual information in our Pinecone indexes. And we have the RUs and WUs. So RUs are basically the read units, which measures the resources used by read operation, like such as query, fetch, and list. This is pretty fast. When you search an index, we will be using the read unit, and when we measure the resources, like for example in indexing, ingestion, and updating, update and delete, we will be using this write unit. So let's create our first index in Pinecone to store some contextual vector embeddings in our Pinecone index. So we will click on this create index, and it will gives us some configuration, like we have some available embedding models, like for example llama text embedding v2 model. Then we have the multilingual e5 large model used for 5 million tokens, and the dimensions. So it's very important to understand the dimensions. Every model has a contextual window size, so that means you can have a vector dimension of up to 1024 2048, and it starts from 384 and goes up to 4096. Pretty amazing, right? So every model has its own dimensionality, and you need to make sure for which model you are using the dimensions for, and you need to select your configuration before selecting the embedding model. So we will be using our manual configuration here, because we will be using our Ollama 3.1 latest model to have our own embedding model, which has a context window of 4096, and the dimensions are 4096. So we will give the name of the index as building rag. This is our Pinecone index name, and once we give the name of the index, we will come to this point where we will select the vector type. So we will be using the dense and sparse. Vector type basically supports, there are two types of vector, one is the dense and the second one is the sparse. So we will be selecting the dense vector type. Then we will select the dimension, the length of the vector. Basically, larger the dimension are, the larger the model it will require. So we will write 4096 as the dimension of llama 3.1 is 4096, and the metric will be cosine. There are basically a metric used for the similarity search. One is the cosine similarity search, second one is the Euclidean, and the third one is the dot product. So we will be selecting cosine similarity search, which is quite fast in fetching data from Pinecone. So, and then we will use the capacity model. So Pinecone indexes are serverless indexes, which supports the data storage reads and writes. These are a serverless based model, which do not requires you to go underlying in infrastructure of your virtual machines. So we will set this to, this is by default set to serverless. All the indexes are serverless, and the cloud provider it is going to be AWS, and the region where you are going to host your index. So we will select this one, which is the Virginia, closest to us, US East 1. This is the region location where we will be hosting our index. So we will click on the create index, and our index will be created in few seconds. So it might take some time depending upon your internet connection. So our index has launched successfully. It is showing the green signal that your index has been launched. So once our index is launched, we will copy this index name and the API key which you have created you will copy the API key and the index name, because in order to access this index you must have an API key available to you to access the specific index. Now let's jump to Python code and start developing. So I am here in my Jupyter notebook. Before we understand this code, I have a PDF file, and this PDF file consists of some company information, which it contains some contextual data of a company known as AI Cortexo. This is the description for the company and the expertise for the companies and the core capabilities of the company. So this is a PDF file, and we are going to ingest this PDF file using the Llama 3.2 embedding model to store this PDF textual data and convert this PDF textual data into embeddings and store all the vectors in the Pinecone index. So let's get started. First of all, we will import our Ollama library, which is an open source library used to interact with the Ollama models. We will run this and make sure you have the selected Python 3.1.27 library and you have the installed dependencies in available on your Python IDE VS Code environment. So it's simply you have to install pip install Ollama, and then you will be able to use the Ollama dependencies. Once it's done, we will use the Pinecone dependencies to interact with the Pinecone and ingest our data in Pinecone. Make sure you also have a .env file which will have your Pinecone API key, and this is going to be used for interacting with the Pinecone. So make sure you have your Pinecone API key in your .env file. Once you have your Pinecone API key, we will run this section, and this will start interacting with the Pinecone serverless environment, which we have already built an index. Just we need to start communicating with our index. So make sure you give the access to the Pinecone API key, and once it's done, then we have created a function where we are going to load our PDF file, and once the PDF file is loaded, we will pass the PDF file to this function, and we will be using two concepts over here. One is the chunk size and the second one is the chunk overlap. So it depends upon your use case what chunk size you are using, but for now as a default I am using the chunk size 500 and a chunk overlap 200. So chunk size is basically, chunk size tells you in the how many chunks and how many sections you want to divide your data. So the chunk size is 500, so your data will be used as converted into 500 descriptional chunk size values, and the chunk overlap is basically the distance between the chunks. So once it's done, we will be using our PDF path passing in our main function, which I will be showing in the last section. It's pretty easy and straightforward. Then we will be using the TQDM Python dependencies, which allows us to give some UI on, or once the code is run, it gives us a UI of a print statement that some text is getting printed on the screen. So we will be using the descending function by extracting text, and then once the text is extracted it will go into a loop and in an increment state by extracting some text from the PDF file. So once it's done, we will be using the LangChain text splitter recursive character text splitter. Basically this is used for splitting text by recursively looking at the characters. So it basically split the text by different characters to find one that works by the nearest neighbors. So we will use the recursive character text splitter function, which requires the chunk size, chunk overlap, and the separators. You want to separate the words by the next line, by spaces, or with these colons. Once it's done, we will then use the splitter dot split text to split the text from it. And once the recursive characters text splitter is run, we will store all those chunks in this chunk variable. So let's run this and let's see. We successfully run this function, and we will be calling this function in our main function in the last step. So now this function is used for creating the embeddings. So let's open our command prompt and see, do we have the embedding model available or not. So I will write Ollama list, and earlier I downloaded the Ollama 3.1 latest large language model, which consists of the embedding model as well. So this is the embedding model, and also we can call this as a large language model also. So this can be used for chat purpose and also for the embedding purpose as well. So if you want to use it for the chat purpose, so you will have to just copy this command and write Ollama run your this llama 3.1 latest model. So this model will start running on my local machine. I have a GPU on my local machine, so this llama 3.1 latest model is currently running as a chat based model. So for example, if I type hi, how are you, it will start giving me output based on the prompt I have provided. So we won't be using it as a chat based model, but we will be using the llama 3.1 as an embedding model. For the chat based model, once our embeddings are created, then in the last step we will be using the llama 3.1 latest model as a chat based model. But for now we are using this function for creating embeddings. So this function is basically responsible for creating embeddings for your PDF file. And what these functions require is that the chunks you have created in the last step, and those chunks will pass to this function and the model name, which is the llama 3.1 latest model. So we will be using the llama 3.1 latest model for the embedding purpose. Then we will create a list of embedding, and this list is going to be appended in the end by storing the vectors in this embedding variable. So we will write a loop where we will basically for every chunk in TQDM chunks, we will be basically creating embeddings for our chunks. So this loop consists of, by calling the Ollama.embedding method, where we are passing our model name and the chunk. So once it's done, we will run this, and we will use this function in the end to pass our created chunks in this function. So once the chunks are passed to this function, for every chunk vectors will be created, and I will show you how these vectors are getting created in our Pinecone index. So currently we don't have any vector store in this index. So let's copy this index name, and we will use this index name in this function. So basically I have created this function to upload our embeddings to our index name. So our index name is basically building rag, and this function requires some parameters, which are chunks, embeddings, and index name, and the batch size. So we are passing a batch size of 50 to not to take too much time, and to pass it by batch. So once we pass these variables to this function, we will call the pc.index method to call our index name, which is the building rag, and we have created an empty list of vectors where we will be storing our vectors in this list variable, and I have used a for loop to go from for I chunk embedding in enumerate zip chunks embedding. So basically this loop is doing a job of passing every chunk. For every chunk it is implementing a for loop, and once it checks for every chunks, those chunks are converted into embeddings through this function, and once the embeddings are done, we will name them as our based on these three variables. One is the id, second one is the value, and the third one is the metadata. So id is going to be the chunk area. For every chunk there will be an id, and for every embedding there will be a value, and metadata is basically the information for every text. So in our pdf file, this, for example, this is one chunk. So this one chunk will have a id of, for example, 0 or in the start, and the values will be these vector these text. Once these text are converted into vectors, every text will have its own vector that is going to be the value, uh, and the metadata is going to be the information about this text, like where this pdf is stored and what this pdf is about. So once it's done, we will print the command for upserting some number of vectors into our pinecone, and once it's done, it will use the index.upsert method to ingest our vectors in a form of in a batch size of 50, and this index.upsert allows us to ingest and upload our vectors to pinecone. Let's run this and call this function in our main function. Then we have the test retrieval function. So once our data is uploaded to pinecone, now we will be using our retrieval model, RAG model, where we will be interacting with the pinecone index and communicating with the pinecone index to bring some data based on our input query. So this function is responsible for bringing some data from pinecone. So before we understand this, let's understand a concept. For example, we have a query. What is the pdf file about? So this is the query, and we cannot pass this query directly to this retrieval function because the retrieval function doesn't know what this query is about, because this is in English language. What is the pdf file about? And these are our tokens. So as we discussed in the presentation earlier in the first lecture, that these tokens are going to be first converted into vectors. So this query is going to be converted into some embedding. So we will be using ollama.embeddings. Let's have an embedding variable, and we will use ollama.embeddings, and this query is going to be passed through this embeddings function. So obviously the RAG retrieval augmented generation works in such a way that first your query needs to be converted into some vectors, and the cosine similarity search works on your input query and the vectors stored in your vector database. Then the similarity search works. If you are not converting your query into an embedding, so the RAG retrieval augmented generation is not going to work, because the cosine similarity works in such a way that there must be a communication between uh, two models. One is the embedding model and the second one is the chat model. So once you have your query converted into embeddings, then we will have two things. One we will have our query of embeddings, like for example 0.01, 0.02, we will have some vectors, and then we will we will be doing some cosine similarity search by using this index.query, where we will using top k, and top k is basically how far every vector is from each other. So we will be using the distance for every vector equal to 3. So once our query is converted into a vector, we will simply pass that prompt. For example, whatever we have asked, that question is going to be converted through this Ollama.embedding function, and once it's done, we will be using some cosine similarity search, like for example index.query. So on the back end we have some similarity searches, so we selected the cosine similarity search in our index, so we will use the index.query and we will pass our embedding. This Ollama.embedding is going to be passed, and once it's passed, then we will call this below. Then we will have some context. The context is going to be our question and answer, and that context is basically going to be our contextual information of what our question and answer is. Then we will specify the role for this Ollama.chat model. So we will be only using one role, that is the user role, and passing our prompt to this Ollama.chat. So the model name is going to be Llama 3.1 latest model, which is going to be our RAG based Ollama model. And once it's done, then we will be able to see what results are being generated through this Ollama.chat model. Let's run this and call this in our main function. So first we are going to use our load PDF method function. If we click on it, we are going to call this main, we are going to call this load PDF function in our main in this code area, where we are just passing the path of the PDF file, which is this, and then we are passing the PDF path to our load PDF function. So let's run this. This will print some TQDM as we use. This will print some UI on the Jupyter notebook. As it is printing, first of all it is saying that we are loading the PDF file, then extracting some text from the PDF file. Once it's done, it will create some chunks based on our chunk size and chunk overlap. So it has successfully created 13 chunks. So if you want to see what our chunks looks like, so we will print the chunks. So this is our chunks, and basically this is our contextual PDF data stored in these chunks. This is not a big thing to worry about. This is just our text. Now we are going to convert this text into embeddings. So let's pass these chunks into our embedding function and let's see what happens. So now we are using our Ollama 3.1 latest model, which is running in our background. So if you want to see which model is running, you will just simply write Ollama PS, and our embedding model is running and using 16% of the CPU and GPU. So now once we analyzed how our chunks looks like, we are going to pass these chunks into our embedding function. So let's run this. And this embedding function requires some chunks, and we will be using the Llama 3.1 latest model, which is currently running here, and this is taking some CPU and GPU computations, and the context window is 4096. So let's see how our embeddings looks like. Let's print those embeddings. So basically our resulting embeddings looks like this. So as I have told you, that these chunks are converted into vectors. Every chunk is now converted into vectors successfully, and once they are converted into vectors, we are going to store these chunks and vectors into our Pinecone index. So let's pass these embeddings and chunks to our upload to Pinecone function. So this is going to upsert and ingest our chunks into our Pinecone index. So let's refresh this and see whether it has stored our chunks or not. So I have reloaded the page and it has successfully stored our whole chunk of data into our Pinecone index name, which is the building rag. So once it's done, we will now pass our query to our test retrieval function over here, and this query is going to be converted into embeddings, and then once our input query is converted into embeddings, then two things are going to happen. One is the user input query embedding, and the second one is the Ollama 3.1 chat model. So the cosine similarity is going to happen between these 2 points. One is the input query embedding, and the second one is the Ollama chat input query. So let's run it and see what happens. So my query is, what is the AI Cortex about, what is this file about, and it will tell me some information about my query. So this is a RAG based model, and this retrieval augmented generation is going to return some information based on my PDF file. So this PDF file is basically has some information, and our input query was, what is the AI Cortex about. So it has successfully the retrieval, my test retrieval function, my Ollama 3.1 RAG based model has successfully brought up some data from the Pinecone index over here. So this means that we can build our own retrieval augmented generation model based on our own internal data. So the beauty of this whole architecture is that you can build your own internal RAG based AI assistant models and bring data from Pinecone vector databases and build your own RAG based model. So the beauty lies over here is that you can build your own internal based AI agents on your own internal AI data. So this means that we can fine tune our own model on our own internal database knowledge. Thank you very much, and make sure you experiment around and test this whole Jupyter notebook on your own PDF data. And the second thing is that most of the large language models are trained on large corpus of data on Wikipedia, on different available resources on the internet. So that ChatGPT, Bard and Gemini is not going to give you answer on your own data, because they don't know about your data. So you want to make your own AI agents, so then you have to train your AI agents on your own data. You have to follow the RAG based concept, which we have implemented here successfully. Make sure you run these set of codes and experiment around, and you have your own Pinecone API keyset.env file. If you face any issue, do let me know, and we are going to build amazing AI applications in the next upcoming lectures using Ollama framework. Thank you.